Hi everyone, welcome to this preface video for Module 10 of CNEES 7103. We're going to be talking about models with non-independent errors in this module, which is coming out of Chapter 11 from your textbook. And there are a number of considerations that we have to take into account here. And in some of the subsequent lectures, we're going to be delving into these topics in much more detail. But I wanted to start with this sort of overall primer lecture to give you a sense of how what we're doing is really the same, but we just have to apply it to a different level of analysis in our data. A lot of the same model building approaches, developing contrast codes, calculating sum of squared errors, and then determining how much variance we've actually explained remains exactly the same as what we've done before. But now we just have to apply it to new levels of analysis or account for variation at different levels of our data in order to examine our treatment effects more clearly. So in our assumptions thus far, we've talked about models where we have, a series of betas for the parameters that we're estimating being multiplied by either a continuous x variable or some kind of contrast-coded categorical x variable. And in all these models, we've made important assumptions about the residuals, which are represented by the epsilons in the equation above. And we've said that these epsilons have to be relatively normally distributed. They have to have a relatively constant variance, and they have to be independent of each other. We're going to talk more about these first two assumptions, how much we can violate them and what we have to do if they are violated in the later chapters when we're talking about models with poorly behaving or ill-behaved error terms. But this third assumption is actually really central, and it's actually the worst of the assumptions that we can violate. Because if we violate the assumption of independence, that's generally going to have the largest effects on the robustness of our model and how accurate our p-values are. So if we assume that these things are independent when in fact they are not, that can actually lead us to making substantial inferential errors, and we'll often have a completely different conclusion than if we correctly accounted for the statistical dependencies in our data. So it's going to be really important that we understand how to identify these statistical dependencies and then learn how to account for them. And by and large, we won't have to do these things by hand to nearly the same extent that we're going to be doing in this course, because in the future, right, we'll sort of identify the appropriate design for our analysis, and then we'll implement these things on the computer. But for now, it's important that we actually be able to understand how we're controlling for these statistical dependencies, how we remove that variation from our ANOVA table, and then how we actually calculate the variance for the effect of interest. So statistical dependencies, as we'll talk about in more detail, arise usually from things either being grouped or things being sequential. So for instance, if we're measuring data from partners in the same couple or measuring data from children in the same classroom, those are grouped data. Children in the same classroom are likely to have more similar test scores from children in different classrooms. Now, similarly, if we're assessing data from patients at different times, those are going to be sequential data. And time 1 is more similar to time 2, is more similar to time 3, right? And the farther and farther out we get in time, the less likely or like each other those data points probably are. Now, similarly, we might have animals repeatedly measured under different conditions, and that actually might introduce both a grouping effect and a sequential effect, because they have different conditions, which creates a grouping, but if they're repeatedly measured, that creates a sequence, right, and there's an actual time effect there. So we might have dependencies due to grouping, due to sequencing, or due to both in our data. The other thing then that we have to think about now is when we're looking at these different time points or repeated measures is that they actually create different levels in our data, because we can look at things at sort of the higher order group level, the lower level person level, or we might have time within people. And depending on your research design, you can think about your data being represented at each of these different levels. And our manipulations are going to happen at different levels of the data. So because our manipulations happen at different levels of the data, we need to partition the variance into different sources to correctly say where is our model explaining this variance. Because if we have a manipulation that happens within subjects, we don't want to try to explain the between subject variance. We want to try to explain the within subject variance. And the person is usually the level of analysis in our experiment. So we'll often refer to variables as either a between subjects variable, that is, it varies between people, or a within subject variable. So that means it varies within a person. So in sort of a traditional context, right, in a randomized controlled trial, we might give one experimental drug to the treatment group and a placebo to the control group, and you're only in the treatment group or the control group, so that's a between subjects variable. Alternatively, we might actually alternate between two different types of drugs that we're testing. So the same person is going to get drug A and then get drug B. And so if we alternate drugs within a person, then that's a within subject variable. So we might have between subject or within subject variables depending on our research design. And we need to be able to identify at which level this manipulation is happening, because that's the level at which we want to try and explain the variance. So this also means we need to partition the total variance into both the between subject sources and the within subject sources to understand the effect of our manipulation. Because if our manipulation happens within subjects, we only want to focus on that within subject variance. To illustrate this sort of conceptually, let's imagine that I have some outcome variable y as a function of the independent variable x, which is a contrast-coded predictor to represent if you took drug A or drug B. So in this example, let's say that drug A was coded as -1, drug B was coded as +1, and you can see that here are individual data points, and here are the means if you actually calculated the means for those data. So it looks like drug B is doing a little bit better than drug A, and assuming that positive y is good, but there's also a lot of overlap in our data. But now, let's actually think about if this was a within subjects research question rather than a between subjects research question. So that is, rather than having one group get drug A and one group get drug B, the same people actually got both drugs, just at different times. So if we recognize that these data come from the same people at different times, what we're saying is that our manipulation is actually happening at the within subjects level. And these data then are actually paired to each other, right? And so we can draw a line to represent that these two data points come from the same person, these two data points come from the same person, right? These two data points come from the same person, and so on. So we're going to actually now have different sources of variance in our data. We're going to have between subjects variance, but we're also going to have within subjects variance. The between subjects variance tells us, on average, are you a person who has a high or a low value of the dependent variable? And the within subjects variance tells us how much did you vary as a function of what drug you took. So we need to account for the individual differences in our data. And then by removing those individual differences, we can remove the between subjects variance. So we can, rather than having just y, let's now think about this as, we'll call this yc for centered, where I take the score for each person under each drug type, and I subtract off the average score for each person. So now, on average across levels of x, we have the average level of y, which is 0. So that means we took the mean away from each data point for each person. So at the average level of x, yc is equal to 0, which means that each person is on their average. So now if you have positive values of y sub c, that means you are above average relative to yourself. If you have negative values of y sub c, that means you are below average relative to yourself. And by removing each subject's mean from their data, we can actually see how that affects the distribution of the data points, and we actually get this tighter clustering of data points for both drug A and drug B. Now when we actually draw those means on there, with that between subjects variance removed, we can actually see the treatment effect more clearly, and it's actually larger relative to the amount of variation that there is in the data. So we actually can see the within subject treatment effect now, because we've removed the between subjects variance from our data. And by removing that between subjects variance, all we're left with is the within subjects variance, and out of that total within subject variance, we can say how much of it is explained by which drug you took. So when we put this into an actual ANOVA table, right, we might have something like this, where we have the total amount of variation in our data. And if we just looked at how much each data point varied around the grand mean, right, that would tell us the total amount of variation within the data. We can further break that total, though, into the total within subject variation, right? How much variation actually occurs within the subjects in our experiment, and the total between subject variation, to say how much variation actually occurs between subjects in our experiment. So by breaking that into two different sources of variation, right, we have the between subject variance and the within subject variance, and we might have variables that operate on different levels. And the between subjects variables need to explain the between subjects variance. The within subjects variables need to explain the within subjects variance. So within both of those sources then, right, once we have isolated the total between and the total within, we could actually look at different variables and see how much they reduce the variation in our model. And this is exactly the same thing that we've done since, all the way back in Chapter 3, where we're looking at how much variance is reduced by a particular variable, right? So we might have a continuous x variable or a contrast-coded x variable, but we're going to put that into the model, look at how much of the total variance it reduces. The only difference is now that we have different types of total variance it could reduce. If it's happening at the between subjects level, it reduces the total between subjects variance. If it's happening at the within subjects level, it reduces the total within subjects variance. Right? And in this example, let's say that we actually had two between subject variables, so that's x1 and x2, and one within subject variable, so that's x3. So by putting those variables into the model, we can say what its sum squared of errors is accounted for by x1, what sum of squared errors is accounted for by x2, what sum of squared errors is accounted for by x3. Now, x3 feeds into the reduced within variance, right? How much of the within subject variance did we explain? x1 and x2 will both go into the reduced between subject variance, and how much between subject variance did we explain? Now, after explaining that variance, we're still going to have some error, right? So the sum of squared errors of the residuals, right, will be the unexplained variance left at the between subjects level here, but we'll also have a sum of squared errors of the residuals for the unexplained variance at the within subjects level. So we need to be able to account for the statistical dependencies in our data in order to isolate the level at which our different effects occur. So you can think about this, right, kind of with the graphic that we've shown here, with the red circle being some sort of grand mean or the overall mean. The green dots might be each subject's mean, and then the blue dots might be that subject's mean in each condition, right? So I can explain variation away from this red dot to explain total variance. How much individual participants vary away from that red dot tells me about the between subject variance. And then how much these blue dots vary around the green dots tells me about the within subject variance. So I can explain those sum of squared errors at lots of different levels, and the number of levels I have might change based on my research design. So now the book shows us a way of doing this by calculating within subject weights that as a transformation of the outcome measure. So they show you how to calculate these W weights that give us basically a new outcome. And we might have weights that represent the within subject average, the within subject difference, right, or the within subject quadratic effect. And essentially those weights take on values very similar to contrast-coded predictors that we've dealt with before. Now that is a perfectly valid way of doing this calculation, and it will give you the appropriate sums of squared error tables. But I think an equivalent method that I prefer, because I think it is more understandable and more straightforward, is actually accounting for the mean of each person or each condition or each person in each condition, depending on your design. And it makes our formulas a little bit different, but in the videos that I'm going to use, I will show you how to do those calculations using those formulas. And we'll do an example with a nested design, and we'll do an example with a cross design, and I will walk you through those examples from the textbook. So as you're reading the textbook, I would like you to read all the way through the chapter, but when you encounter those W's and we're calculating those weights, don't worry too much about those formulas, don't worry about the actual implementation, because I'm going to show you an alternative method for calculating the sum of squared errors that we're going to use. And we're only going to use those calculations in our first lab. So I'm going to ask you to walk through the same calculations that I do in the next series of videos by hand. And that will give you a good understanding of how you can perform them on your own when you have a repeated measures ANOVA. In general, though, if we're dealing with a repeated measures design or we're dealing with a mixed design, when we have variables at both the between and the within subjects level, these calculations are going to get pretty complicated, and you're not going to be asked to do these things by hand. So doing them by hand is an important first step to build up your understanding of how these calculations work. But as we move forward, it's going to be more important that you have a conceptual understanding of your study design, conceptually understanding what partitioning the variance means and different sources of variance in your experiment, and then how to interpret the results that you get from a statistical program. So in the second lab, we're going to use R to run statistical models with either multiple repeated measures or using mixed designs where we have some repeated measures that vary within subjects and some measures that vary between subjects. Right, and you can also then get a mixed factorial ANOVA table that you'll have to interpret. And our focus in that lab will be on interpreting the statistical outputs and understanding the different variables rather than the by hand calculation that allows us to isolate the variance at different levels. So please read through the chapter. Like I said, if you can get through everything, it would be very helpful for your understanding moving into the lab assignments. And feel free to email me with any questions that you might have. But again, we're actually going to present the formulas in a slightly different way than calculating these within subject beta or these within subject W weights that are a transformation of the outcome measure. Now, it is perfectly valid, and statistically, these two methods will be equivalent. So if you have further questions about the formulas that I present in the subsequent slides or formulas that are presented in the book, please let me know, and we can try to set up a time to meet virtually, or we can try to hash out those questions over email.